Hello everyone, I am Akhilesh Kumar Srivastav from ABS Engineering College, Ghaziabad. In the series of operating system lectures, we were looking at the memory management schemes. In the last term, we have seen about the contiguous allocation, and in the contiguous allocation, we have seen the fixed size partitioning. Fixed size partitioning has several disadvantages. We will start today's lecture with that, and then we shall go with the other scheme or other suggested scheme that does the better utilization of the memory as compared to the fixed partitioning. Now, the outline of today's lecture will be that we will first see the background of the memory management. This is the first thing that we should see in every lecture of the memory management, and we will see that the logical and the physical addresses have a role to play. Then we shall see the memory the multiprogramming with fixed partitioning. Then we will also see how can we deal with the free and the allocated spaces, and then we will see how should we utilize the memory in a better way when a lot of wastage is coming up. So, with that will be done with the help of the compaction. Now, this was discussed in the last turn as well. Let us have a just quick recap of this, that whenever memory management component has to be handled, then we should have a picture in the mind that every process can be executed only if it is brought to the main memory. So, the transition of the process should take place from the hard disk to the RAM or hard disk to the main memory. Then CPU can have the direct access to the RAM and the registers, but CPU cannot have the direct access to the hard disk. This is region of bringing the process in the RAM is this only, that CPU cannot have the direct access to the hard disk. Now, whenever the instruction has to be read from the main memory, it can involve several CPU cycles, and CPU actually gets blocked whenever the reading operation from the main memory is being performed, or even the writing operations. During the writing operation also CPU gets blocked and does not do anything than doing the writing operations. Similarly, when the instruction has to be read from some CPU register, it requires only one CPU cycle. There is a memory involved in between the RAM and the CPU, that is known as the cache memory, and cache memory keeps all those instructions which are frequently accessed. Okay. So, whenever let us say it is a program and the program contains 1000 instructions. Out of the 1000 instructions, if I am at the first instruction only, and if I am executing the first instruction at the moment, it is very likely that the second instruction will be executed next. Third instruction will be executed after the execution of the second instruction. So, usually the instruction execution is sequential. So, when CPU is referring to the main memory, it will be doing nothing but referring to the main memory only. So, for the next instruction also CPU, if CPU is going to the main memory, it is wasting a lot of time. Okay. So, what is done that a block of instruction or the bunch of instruction, let us say the size of the bunch is 100 bytes or 100 instructions. So, this is brought to the cache memory, and the CPU refers to the cache memory. The cache memory is very near to the CPU. So, cache can be accessed faster than the main memory than by the CPU. So, CPU first refers to the cache memory. So, if the instruction is present in the cache memory, CPU gets it from here, but in case not, then CPU refers to the main memory, and again the next bunch of instruction will be brought from the main memory to the cache. So, this is said that the execution of the instruction is taking place, or the reading of the instruction is taking place from the cache itself for the CPU. Now, if you are bringing multiple instruction or block of the instructions, bunch of the instruction from the main memory to the cache memory, obviously this several CPU cycles will be required, and we require multiple addresses also. So, whenever the read operation has to be performed, the memory unit will seize at the series of the address plus a read instruction, and if it has to be written, it sees it at the series of the address plus the write instruction. Fine. Now, whenever we are dealing with the RAM management, we should also deal with the cache memory management also. If the changes have been made in the cache memory, then that changes should be reflected back to the main memory also. So, there are some write policies which are being involved, write through, write back policies. We shall discuss that in the later lectures or subsequent lectures. Now, whenever we are dealing with the multiple partitions, it has already been discussed that the OS region is different and user region is different in the main memory. For example, let us say this is the replica of the RAM, this is representing the RAM. In this RAM, this is the OS region, let us say, and let us say this is the user region. There are many processes which are there in the user region. Every process has its boundaries. If the processes are, let us say, P1, P2, P3 and P4, then P1 has some region, this is the region of the P1, this is the region for P2, this is the region for P3 and this is the region for P4. P4 will not like that P3 should interfere in the region of P4. Similarly, P3 will not like that P2 interferes in its region and P4 interferes in this region. So, the strict boundaries have been defined for these processes. So, for check of the boundaries or for the check of the addresses, that whatever address we are referring to lies in the well limit, we need the support of the registers. One is the base register and one is the limit register. So, this is the additional component or additional requirements for protecting our memory. So, the memory protection is very important portion of the main memory management. Now, we have also discussed about the logical and the physical address. Just have a quick recap of this as well. Whenever CPU is referring to any instruction, CPU will think that the addresses start from 0. Let us say the size of your process is 100 bytes. So, the addresses which will be ranging will be from 0 to 99. 0 is the smallest address and 99 is the highest address. Any address in between 0 to 99 is the logical address for this process, and the space of the address 0 to 99 is called the logical address space. Fine, this is called the logical address space. So, 0 to 100 is the logical address space, and any address in between will be the logical address, and we sometimes call it as the virtual address as well. Now, this process will get accommodated somewhere in the main memory. Let us say this is referring to the main memory. So, in this main memory, your process may go in some address, let us say that address starts from 20,000. So, your first instruction is at 20,000, since the size of the process is 100. So, the last instruction will be at 20,099. So, this region 20,000 to 20,099 is known as the physical address, or any address in between, this is the physical address, and the physical address space for this particular process is 20,000 to 20,099. However, for all the processes in the system, the addresses will be ranging from 0 to the memory size. Let us say the memory size is 10024, then the last address will be 1000243. So, the logical address space actually is from 0 to 1000243. So, logical address space and the physical address space. Whenever the CPU refers to the instruction, that needs to be converted to the physical address. So, we also have discussed about the multiprogramming with the degree of multiprogramming varying, and we have seen that the main memory can accommodate limited number of processes, but to keep the CPU 100% busy, we have to bring infinite number of the processes to the system. So, it means that there is no limitation of the CPU, or CPU cannot be kept 100% busy. So, if we want to keep the CPU 100% busy, then we will have to bring infinite number of the processes. We have discussed about the contiguous allocation schemes, where when a process is accommodated in the main memory, it should be given the addresses in the contiguous region. For example, if my process is of size 100 size or 100 bytes, if the starting address is 200, so my process should be accommodated fully in between 200 to 299 address. So, this is the contiguous scheme. What may be the non-contiguous scheme? We may divide this process into the several chunks. Okay, let us say each of the chunk is of size 20, and these 20 size chunks are accommodated in the different portion of the memory. So, that will be non-contiguous allocation. Okay. So, the contiguous allocation says that we have to accommodate our process in the one contiguous space only. Okay. We have discussed about the fixed partitioning schemes. There are two fixed partitioning schemes. One is the equal size partitioning. In the first, we are restricting that the degree of multiprogramming is 4 and each of the partition is of size 100 kb. The other scheme says that we should divide our memory regions in the unequal size partitions. So, here we have a partition of 500, 200, 450 and 600. We can accommodate the processes here, we can accommodate the processes here with the various schemes. For example, first fit, best fit, worst fit scheme and next fit scheme. We have discussed them very well. In fact, these will be discussed today also for the dynamic partitioning schemes. So, we have seen that the best fit algorithm makes best use of the memory whenever we are dealing with the fixed partitionings or multiprogramming with the fixed partitions or multiprogramming with unequal size fixed partitions. Now, whenever we now are going for the dynamic partitionings, and the dynamic partitioning scheme says that you divide the memory or you divide the partitions or you create a partition only if it is required. So, the memory is assumed to be a single chunk, and as soon as the memory is required, then only you should create the chunk, otherwise you should not create the chunk. Okay. For example, if this is the memory, let us say, and in this memory this is the OS region. Let us say the user area is of size 5000 size. So, 5000 size user area is considered as a single hole, where any process can be accommodated. Okay. Let us say a process comes, process is of size, let us say 1000 bytes. Then you will create a partition. You will create a partition here, you will put a process here, let us say that this is P1 process. So, the lower region of memory is occupied by P1 and the higher memory regions are free, that will be again a hole of size not 5000 but 4000. Okay. Similarly, if a new process comes, let us say a P2 process comes and the P2 process is of size 3500 size. So, again from 4000 another chunk of the memory will be, or another partition will be created and we will be accommodating a P2 process here. So, this will be of size let us say 3500. So, another 500 size will be free for us, this will again be a hole, fine. So, whenever the partition is required or whenever the main memory is required by a process, then only create a partition. If not, then the rest of the part is treated as a whole or a single chunk. Now, what are the information that we need to maintain in this case? What is the starting address of? Obviously, when P1 is accommodated, I need to know what is the starting address of this process, fine. Then what is the size of the process, size of the partition, what is the size of the partition? It means what is the size of the process, what is the size of P1 or what is the size of the partition, means the same thing. Okay. So, we may be thinking of what we discussed in the last time also, that let us store it here in the base address, the starting point, the size of the partition let us store it in the limit register. So, per process base in the limit register has to be maintained, and then status of the partition, is this occupied or is this a process. So, we may with the time or over the time we may have several holes. Okay. So, either a process will be there in some partition of the memory or that will be simply a hole. So, we need to know that which partition of the memory belongs to what status, is it a whole or it is a process. So, status of the partition should be known, and allocation area table means in which area of the memory I have the processes allocated. We have multiple processes allocated in the main memory. So, we should have a record of all those. So, that is actually maintained in the allocation area table, and similarly we should have a free area table also, that which area are free for accommodation of the new process, we should refer to that table only. If a new process is coming, we will have to refer to the free area table for accommodation of those processes. Now, when we are referring to the fixed partitioning and when we are referring to the dynamic partitioning, there is a slight difference. In the fixed partitioning, let us say we have 3 partitions of unequal size 200, 500 and 700. A process P1, P2 and P3 comes, size of the P1 is let us say 400 and we are doing the first fit scheme for allocation, and P2 is of size let us say 167 kb and P3 is of size let us say 604 size. So, P1 will be accommodated here, P2 will be accommodated here and P3 will be accommodated here. By accommodation of P1 of size 400, there will be a fragmentation of 100 size here in this partition. Similarly, for accommodation of P2 process here in this memory, there will be a fragmentation of 33. So, I am noting it down here. Now, similarly, if we accommodate P3 process in last chunk, there will be a wastage of let us say 96 space. Okay. So, there is a wastage of 3396. So, this is the sheer wastage of memory, we cannot accommodate any process here. So, this is the internal fragmentation. Whenever we are referring to the wastage of memory which is not usable, so that actually means this is the internal fragmentation. In case we are able to use the memory, that will be the external fragmentation. For example, what we are using here in the dynamic partitioning scheme, let us say we have some processes accommodated here. This is the user view of the memory and let us say P1 process is here and then there is a hole, then let us say this is a P2 process and then there is a hole, let us say this is the P3 process and this is the P4 process. Now, you can see that there are two holes here, this may be of the different sizes, let us say this is of size 100 and let us say this is of size 240. So, both of these are holes and any new coming process can get a space here, any new coming process will get a space here or here, okay? Or it may be possible that they do not get a space here. For example, the process size is let us say 300 kb. So, 300 size partition neither can accommodate it in 100 size nor it can get accommodated in the 240 size. So, there is a problem that the cumulative size is 340, but this process cannot, let us say this process is P5 process and P5 process cannot get accommodated in either of these partitions, because their sizes cumulatively is high, but if this is divided into the two portions we cannot accommodate here. So, this is called the external fragmentation. So, if the cumulative size of the partition is able to, or cumulative size of the holes is able to accommodate a process, but they are not in the contiguous space. So, this actually is the external fragmentation. Now, let us take a question and try to understand the dynamic partition well. Here in this question it is said that this is the memory currently, okay? This is the memory currently and this is a process, this is a process and this is a process, and this 150 is a hole and 350 is also whole, okay? Now, the processes or the process requests are 300, 25, 125 and 50. So, these are the process requests and we have to apply various schemes and based on which we will have to answer this, because worst fit, first fit and best fit is being asked here. So, let us solve it with the help of this only. So, let us apply the best fit algorithm. Best fit algorithm will say that we have to go with a technique that has the minimum wastage, okay. So, let us find out for the first partition 300 for the first process 300 out of 150 and 350, obviously 350 is sufficient to accommodate this, okay. So, let us allocate the process number, let us say we are referring this to process number P1. So, P1 is accommodated here in 300 size and 50 is the size of the hole which is created. Since the size of this process is 300, so 50 size hole is created. Then let us say 25 size coming. So, I can either accommodate 25 here in 150 or 50, there are two holes. Since we are referring to the best fit scheme, we will go for the 50 size partition. So, let us accommodate P2 here and there will be a hole again of size 25. Then we have a 125 size process, let us say this is P3. So, P3 can either go in 150 or 25. So, obviously P3 will go to 150 only. So, let us accommodate P3 process here. So, there will be a wastage of 25 space here, this will be a hole. And then last in last we have 50 size partition. So, the 50 size partition can neither be accommodated in 25 size hole here and nor here. So, there are two 25 size holes here, but 50 cannot be accommodated here. There is a external fragmentation here. Cumulatively they will be able to accommodate 50, but they are in the separate region of the memory. Since we are dealing with the external fragmentation, we are dealing with the contiguous allocation scheme. So, 50 size partition or 50 size process cannot be accommodated in any of the partition. So, one of the process has been left. Now, let us solve this problem with the worst fit scheme. You should remember that the 50 size process has not been accommodated. Okay. Now, let us do the worst fit scheme. Worst fit will do the reverse of the best fit. So, 300 size partition will go in 350 size. So, P1 comes here, there is a hole of size 50 here, then 25 will either go in 150 or 50. So, the worst fit says that the maximum fragmentation. So, 25 size process P2 will go here and there will be a hole of size 125, and then 125, obviously 125 size partition is here and there is another partition of 50. So, let us accommodate process number P3 here in 125 fully occupied, then 50 size, obviously 50 size process can come here. So, the P4 process has been accommodated here. So, all the 4 process has got accommodated with the help of the worst fit scheme. Now, let us look at the first fit scheme. First fit scheme says that you should find out the first available slot which is sufficient enough to accommodate your process and fit a process there itself. So, the process 300, obviously it cannot fit in 150 size. So, we will have to go with the 300 size. So, P1 comes here and a 50 size hole is here. Then 25, first fit scheme says that 150 and 50 both can accommodate, but first fit will fit the P2 process here in 150 size partition. A 125 size hole will be created by this. So, next is 125, first hole which is free is 125 size. So, P3 is accommodated here, leaving no free space, and then finally we have 50. So, 50 size partition or 50 size process can get accommodated in the 50 size hole, which is the only remaining with us. So, the memory is completely occupied by the first fit scheme. So, worst fit did fit all those processes, first fit also fitted, but best fit could not. Okay. If we refer to the multi-programming with fixed partitioning, then best fit was giving us a good result, but here the best fit is not giving us the good result. So, first fit scheme is supposed to be the best one whenever we are referring to the dynamic partitioning. So, you should remember it always that the first fit scheme will give us the best result. Okay. Now, let us look at this problem as well. This is pretty straightforward, and here it is said that the processes are coming in some order J1, J2, J3, J4, J5, J6, and their CPU bursts are also given, their sizes are given, and you have to accommodate them in the memory. So, with the help of the diagram you will be able to understand that the total memory that is available to us is 216K. Okay. So, this is entirely a hole. If you will accommodate a 60 size process here, let us say its name is J1. So, from up to 100 it will be busy, and then a hole of size 156 will be created. Then a J2 is there. So, 100 size, again you can accommodate it here. So, you leave with this is 100 size. So, this is up to 256 size partition is there, or 56 size hole is there. Okay. Next is J3 of size 30. So, you create a hole of you create a process space for 30 size, and you remain with 26 size hole. Okay. And then you have 70 size J4. So, obviously for J4 we are not finding a space. We will be finding the space for J4 only if one of the process leaves. So, you can say that at 5 time the J2 process will leave. When J2 leaves, this is a hole, this will be a hole. So, you can accommodate your process of size 70 J4 here in this hole. This hole is of size 100. So, let us accommodate the J4 process here and leaving this a hole of size 30. So, and so on and so forth, whenever a process will leave, a new process will come. Now, here we are taking another question, and this question is saying that 1000 KB memory space is managed using variable partitions, but no compaction. We will discuss about the compaction later. It currently has two partitions of size 200 and 260. The smallest allocation request in kilobytes that could be denied is for. So, there are various process sizes given, and we have to see that which of the process will be denied giving the memory. Okay. So, it is said that we have 1000 KB of memory. Okay. Variable size partitioning is used, dynamic partitioning is used here, and the two processes which are already there in the memory are 200 and 260. So, 200 KB process is there and 260 size or 260 KB process is there. Obviously, 540 KB of memory will be free. So, this 540 KB memory which is free can be like this: 200 size partition here and 260 here, and then 540 here. Can you deny 151 in 540 size whole? No. 181? No. 231? No. 54? No. All these processes can be accommodated here. What may be the other scheme? The other scheme may be, this is a 1000 size, you just keep 200 here and 260 here, then also 540 size whole will be there somewhere in between, and you can accommodate all these processes in the 840 size partition. Okay. Now, let us look at some other scheme then. What you can do that, let us put the two processes in the different spaces. Okay. First store 200 here and then 260 here. So, here you can see that two holes are created. Let us take the holes of the equal size. Okay. So, this is the aptitude one, or this question is more of a aptitude question. So, if you are creating the holes of the equal size, then only we can deny the less size processes. Okay. So, 540, it means this is a 270 size hole and this is 270 size hole. We can accommodate all these processes here. So, this scheme is also not suggestible. Now, let us look at the another scheme. What may be the other scheme? Create 3 partitions of, or create 3 holes. So, how can the 3 holes be created? Let us put a 200 size process here and 260 size process here. Okay. So, the holes are 3. Let us divide the holes in 3 parts or 3 equal sizes. So, let us say this is 180 size, this will also be 180 size, and this will also be 180. 540 kilobytes of memory was free, we have just divided it by 3, so 180. So, 151 size will be accommodated in any of the holes. 181, yes, we can deny 181 size. Okay. Obviously, 231 will also be denied, but 54 can be accommodated. So, we have a conflict in between B and C, but the question is asked that the smallest allocation request. So, out of the 181 and 231, 181 is the smallest one. So, I can say that 181 size partition or 181 size process cannot be accommodated anywhere. Okay. Now, what is the compaction? Compaction is when you are not able to give the memory space to the process, even though if you have the cumulative space higher than the size of the process, since the small holes have been created, they are scattered holes. So, if we bring the small holes together to form a bigger hole and you bring the processes on the other side, then it is said that this actually is the scheme of the compaction. When compaction is done, CPU is continuously busy, CPU is doing nothing, CPU is doing only the compaction, because the relocation of the processes will be required and relocation of the holes will also be required. So, compaction is not supposed to be the good scheme, because CPU is very busy. Okay. So, in case you want to reduce the CPU's time for this, you can do it periodically only, not always, so periodically. Now, there are various data structures in which we should actually store the spaces, or the which would actually store the free spaces and the allocated space information. So, this can be stored in two of the data structures, bitmap and the linked list. We will discuss about this in the next time. So, this was all for the today's lecture. We have the reference for this lecture as Operating System Concepts by the Silverchairs and Galvin. Thank you.